Hello, everybody. Welcome. Come on in. You're in the right place. Hopefully, we'll get started here in just a second. All right, it is the top of the hour by my clock. So, welcome, everybody. My name's Alan Barr. I'm with COEH Northern California, and on behalf of the NIOSH supported education and research centers throughout the country, we're pleased to bring you another installment of the 2026 ERC Ergonomics webinar series. Uh, we offer free monthly webinars on various topics on human factors and ergonomics. This collaborative effort on behalf of each ERC's continuing education program aspires to provide access to current research supported through NIOSH ERC programs. Thank you for joining us today. If you logged in with your registration email, you will receive a link to an evaluation form, and completing that form will qualify you for a certificate of completion worth one continuing education contact hour. A couple of webinars to mention that are coming up on April 22nd. PFAS, Research and Community Engagement to Reduce Exposure and Improve Clinical Care. And on May 12th, we have Examining the Role of Motivation in Occupational Health and Safety, Insights for Research and Practice. You can register for those webinars and others at coeh.berkeley.edu/webinars. For today's webinar, if you would like to ask a question, and as always, we encourage you to do so, please enter it into the Q&A, and we'll save time at the end of the presentation to answer those questions. There will be two presentations today, essentially one, but one after another, sequential presentations. Today's webinar is being recorded and will be made available along with past webinars on the COEH Northern California YouTube channel. In support of our work, please take a moment to like and subscribe to our channel, help us grow. A PDF presentation of the presentation can be requested directly from coehce@berkeley.edu. That's coehce@berkeley.edu. Okay, today's topic, human-AI interaction and trust and safety critical domains. As I mentioned earlier, we have two speakers today. First speaker is going to be Duwan Han. Duwan is a PhD candidate in industrial and operations engineering at the University of Michigan. His research centers on human-machine interaction and trust in automation, with an application focus on conditionally automated vehicles, drivers, and pedestrians. He aims to understand human automation behavior and design safer, more efficient, and trustworthy human-vehicle interactions. Our second speaker is Jinyong Kim. Recently, he defended his PhD dissertation in industrial and operations engineering at the University of Michigan. His research is centered on human trust and performance in AI-assisted decision-making, with a primary application in healthcare. His future goal is to conduct human factors research to improve human autonomy interaction for people with disabilities and the aging population. And with that, I will hand the microphone over to Duwan.
Well, thank you very much for the introduction. Hello, everyone. Good afternoon. I am delighted to give you a talk related to my study in toward trustworthy human autonomy interaction. My name is Duan, and I also recently defended as well, and I'll be explaining one of the study that I have been focusing on related to the human autonomy interaction in automated vehicles. So automated vehicles are the vehicles that operates and performs the dynamic driving task with or without the human actively supervising the situation. For instance, you might have seen, as an example, Waymo's autonomous vehicles driving around the city, giving rides to people, even without any driver sitting on the driver's seat and manually driving the situation. Another example will be recently, a few years ago, Mercedes have officially launched their level 3 automated vehicle called the Drive Pilot, which was designed to operate within a certain specific environment. So would all automated vehicles would be the same? The answer to that is there are levels in automated vehicles according to the Society of Automotive Engineers. So I would say not automated vehicles are the same. And according to the standards from the SAE, there are levels ranging from 0 to level 5, depending on the driver role and the driving features of the automated vehicles. As you can see, the traditional interaction that the driver interaction between the driver and the pedestrian was that the driver has access to vehicle dynamics, and also depending on the situation and the information of the situation that the driver has, it can make the decision on its own, and also the driver has access to the behavior such as gaze behavior and gestures in order to communicate with the person outside of the vehicle. However, as the automated vehicle takes in, now the role of the driver changes from the driver to the supervisor. And the automated vehicle is now controlled by the system here. And the role of the driver now switches to the supervisor, where the so-called the person who was the driver now monitors the situation and then assures that the situation is the system is safely driving and then maintain the situation. However, now that the driver is away from the driving task, the driver has limited access towards the behavior that it usually had, which is the gaze behavior and the gestures. And also, this changes the nature of the interaction, where now the driver does not directly interact with the pedestrian, but now the driver can interact with the system, and the pedestrian can now interact with the driver or the system. So this portion that newly changed is the driver-vehicle interaction, as the automated vehicles take over the place of the driver, and also the pedestrian vehicle interaction, that the pedestrian interacts with the automated vehicle. For the time being of today, I'll be mainly focusing on the pedestrian vehicle interaction. So the traditional interaction that I previously explained is that the drivers communicate their awareness and intent with the external humans, such as pedestrians, cyclists, or workers outside of the vehicle, through these three communication methods, such as eye contact, gesture, and also the vehicle behavior, which is extended from the driver's intention. However, now that it has changed to the automated vehicle taking over the driving performance, driving tasks, the driver may have limited access to these communication methods. In order to resolve these situations, there have been two aspects of addressing these situations, which first, research focused on prediction and planning, and second, enabling explicit communication. Prediction and planning, this aspect of research wanted to develop the automated vehicle with more capability of the prediction algorithm, such that the automated vehicles can accurately predict the human behavior. And according to those results, the automated vehicle can plan the trajectories, which ensures safety. Another aspect would be, why not just replicate the situation that the driver and the pedestrian traditionally had, which enabling the automated vehicles, the automated systems with explicit communication method called the external human-machine interface with various modality. Mostly the prediction and the planning and also the explicit communication focused on the conventional automated vehicles, where we dealt with conventional vehicles, and also the situation was limited towards the crosswalk situation, where the conventional vehicle and the pedestrian usually encounters each other in a crosswalk environment. So we our project team felt that we could expand this situation into a more dynamic generic situation, which both prediction and the EHMI enabled automated vehicles can operate, such as a dynamic situation within the manufacturing facility. And such example of the automated vehicle operating within this situation will be the automatic forklifts. So this brings on to the study that I have focused on, which is the external human-machine interface design for explicit communication. Like I previously mentioned, the industrial automated, related to the industrial automated vehicles, advanced technologies are incorporated into the industrial workflows, and manufacturing facilities so that we can promote more efficient and automated situations. These environments in manufacturing facilities are very dynamic with workers and automated machineries working in a shared space with all different components in that shared space as well. For instance, you can see the illustration at the Amazon's immense multi-level fulfillment center, and also one of the illustration that depicts the general situation where they're conveying on conveyor belts, producing goods and products in the manufacturing facility with various machineries around the workers as well. One type of automated vehicle within the situation that I would like to discuss about is the automated guided vehicles, AGV for short. These AGVs serve the purpose of transporting goods and products and enhance operational efficiency by streamlining logistics and minimizing human efforts in repetitive tasks. So the AGV can perform on behalf of the human workers in a small repetitive task, moving small loads of things repetitively, or even carrying heavy materials that human workers cannot. In previous AGV operation methods, mostly were focused on computer-controlled vehicles relying on fixed paths, such as rails embedded into the floor or magnetic bars and tapes attached to the surface. These fixed paths, illustrated by the rails and the magnetic bar and tape, serves as a guidance and reference point for the AGVs to follow along the path, and that will be their path for performing those transporting goods tasks. And since these vehicles were relying on fixed paths, most of the focus were on the efficiency of finding different path recognition that is more optimal, and also trying to optimize the positioning of the paths so that the AGV can optimally operate around the manufacturing facility. However, there are some limitations on relying on the fixed paths, which these fixed paths lacks flexibility and issues in dynamic situations where things could change. Current AGV now, rather than just relying on the guided paths, these AGVs are now capable of navigating freely, relying on sensors as well. So partially, they are relying on guided paths for the reference points as well, but they are capable of getting out of the guided paths and then navigate freely, just depending on the sensors as well. And the characteristic that the AGVs mostly work in isolation with limited sharing of workspace with humans has not changed from the traditional previous AGV methods. And since integrating these two facts, which now AGV has more freedom of movement and operation, and AGVs mostly work within isolation, this could pose some issues that AGVs now more closely work with the workers in a shared dynamic settings that could lead to potential safety issues. So therefore, this project wanted to focus more on investigating on how we can develop the AGV in promoting a safer, trustworthy interaction. There, I would like to introduce two types of communication method, the implicit and explicit communication method. So usually the robots or the systems observe and analyze the human behaviors and motions, and they put these inputs into the prediction algorithm. The system then calculates and predicts all of these through the algorithm and then outputs the results. Based on the output, and the robot or the system will make a decision and then executes the action. However, implicit communication in this whole process do not directly communicate the results or of their prediction or their intention towards the human, which means that human must infer the internal state and actions based on the robot or the system's motion or positioning or their behavior patterns. Explicit communication, on the other hand, is very much similar to the implicit communication from the start, but at the end, now the robot can directly communicate the results of prediction of their intention through externally human-machine interface. So this brings on to the motivation of our study, which we started off from the fact that research on vehicle-human interaction has mainly focused on pedestrian motion prediction, and also mainly focused on limited situations with conventional vehicles and the pedestrians in a crosswalk. So the aim of the study was to expand this situation in a more dynamic settings, and also trying to select the AGV motion states and generate EHMI designs to convey the states. Also, we wanted to compare the effects of implicit and explicit communication in human-vehicle interactions. So if we want to enable the AGV with implicit and explicit communication, we first need to prepare the prediction algorithm, which represents the implicit communication, and also the EHMI designs, which will represent the external communication, explicit communication. So in the prediction algorithm, our study team had a previous project related to developing the prediction algorithm, which is called the finite autonomous model. This model has 6 intuitive states in predicting the workers' walking behavior within the manufacturing facility. And as you can see, the figure on the bottom right left side here has all the 6 states that the workers can show during the walking behavior in the manufacturing facility. And this finite autonomous model can predict the workers' trajectory and also their states based on the information that it gathers from the situation, such as gaze behaviors, the direction of the gaze, and also their location within the floor map of the manufacturing facility. With that prediction model, we also move on to now deciding the states of the AGV behaviors. So based on the 6 intuitive workers walking behaviors states, we have generated 5 behaviors for the AGV to convey to the workers. And you can see the 5 states on the bottom here. And based on these behaviors, we also selected light strip pattern EHMI designs to convey these behaviors. We have went through design parameters such as the number of the light strip patterns, the pattern itself of the light strips, intensity, frequency, and direction. And putting all these together, we came up with 8 different design groups. As you can see the design groups on the right side here with each use parameters for the design groups. In total, we have generated 24 light strip patterns for the AGV to use to convey these 5 states. We then deploy this into the online survey where we have gathered opinions from 97 participants. And these 97 participants all went through 4 blocks of questionnaires where each block contained all 24 designs that we have generated. And each of the block asks the participant, what does the design pattern mean? For each of the design, we have given them multiple choice answers that have 5 states of the AGV behavior. And we have also asked how confident the participants were with their answer. Just in case the confidence level was low, then we consider that answer not to be have the same weight as the response that had higher confidence level. We repeatedly measured these through the 4 blocks, which first to third block, we have asked them to respond based on their quick intuitive judgment. And block 4, we have asked them to take much as time as they want and respond based on their careful and best response. After going through these results, we have selected the top 3 to 5 most frequently selected designs from each behavior state. And then we have selected 1 design per behavior to represent the AGV to convey that behavior. And we have also closely worked with our liaison who has extensive experience in interacting with the AGV and understand the situation between the worker and the AGV interaction. And you can see the results on the bottom here. I think the GIS are not currently moving, but these are all moving components with the light patterns. Now we have prepared the prediction and the EHMI designs. Now we compare the effectiveness of the implicit and explicit communication in our VR testbed, where we replicated the manufacturing facility with the workers can interact with the AGV in this situation. Yep, as you can see, we have put the participants in a VR situation with this omnidirectional treadmill where the workers can walk around in the VR environment and also interact with the components using the handheld devices and observe the situation with the headset of the VR. You can see that the AGV is currently moving towards the worker while the worker is trying to perform a task. So for this evaluation, we have gathered 30 participants, all deploying with the within subject design, where all 30 participants go through 3 conditions, and each of the conditions contains 10 AGV trajectories, resulting in 30 trials per participant. The specific task that we asked the participant to perform while interacting with the AGV in the manufacturing facility was that the participants were required to pick up a toolbox from one station and then move to another designated station, drop it off at the location where it matches the number that the participants need to memorize when they first picked up at the first starting station. And for the 10 AGV trajectories, we have also considered whether the participant or the worker needs to cross the road where the AGV also operates, or where the workers are going to encounter the AGV in terms of front, back, and then going along with the side or the opposite side. Also, we have also considered the AGV, whether the AGV was operated in the closer lane or the further lane in the manufacturing facility. For the three AGV conditions, we have the control prediction, which represents the implicit, and the EHMI plus prediction, which represents the explicit communication. For the control condition, it is the AGV that is currently used in practice, where it has the standard of the boundaries surrounding the AGV, and it decelerates when the participant is in the slowdown zone, stops whenever the participant enters the stopping zone, and it maintains normal operation otherwise. For the prediction condition, now the AGV is capable of predicting based on the algorithm that we have implemented, which the AGV computes its own location and the participant's position at time point starting from 0 all the way to 4 seconds in the future. And if the predicted position of the participants is in the slowdown zone, and if the participant is not in the safe states at time point 0, then the AGV decelerates. The safe states here is referring to the FAM model, which safe states includes at station and approach station. Lastly, the EHMI plus prediction is identical to the prediction, but now the AGV is capable of conveying its intent through the EHMI design that we have selected at the results from the online survey. The dependent measures that we have also gathered are the zone entries, which is the number of participants entering the stopping and the slowdown zones during these interactions. And we have also gathered subjective measures, trust, perceived safety, and performance, and understandability measured in two time points, which is after the trial and after the condition. So as I mentioned, each participant results in 30 trials, which as a total, 30 participants can generate 900 trials. We also asked the participants after each trial whether they have noticed the AGV or not. And amongst the 900 trials, 132 trials were excluded since the participants responded that they did not notice the AGV. So we have continued on with the remaining trials, which is 768 trials. Amongst these trials, there were a total of 14 crashes and a total of 139 slowdowns. We put these data into mixed effects logistic regression models. And both of the stopping and the slowdown model have shown results, as you can see on the bottom here, comparing the prediction and the EHMI plus prediction with the control condition. Based on these results, we have noticed that in the slowdown model, both prediction and EHMI plus prediction have showed lower likelihood of entering the slowdown zone compared to the control condition. For the subjective measures, across all 4 subjective measures, we have seen similar trends where the ratings have increased as we move along from the control, prediction, and EHMI plus prediction. Here you can also see for both post-trial and condition, there's an increasing trend in trust. And when we ran the statistical analysis, we have seen a significant difference between control and EHMI plus prediction, where explicit communication was more trusted than control condition. For the perceived safety, it shows the same increasing trend and also the same significant difference between the control and EHMI plus prediction in both post-trial and both condition. However, additionally, we have also observed that the explicit communication was perceived safer than the implicit communication in the post-condition case here. For the perceived performance, we have also seen the similar trend of the increasing trend, and also not to mention the significant difference between the control and the EHMI plus prediction in both post-trial and condition. However, we have also additionally observed that there is a significant difference between the control and the prediction in the post-condition case. Lastly, in the understandability, we have seen the increasing trend as we move from the control all the way to the EHMI plus prediction, but the statistical analysis did not show any significant difference between these conditions. We have also discussed on why this was happening, and we focused on the previous research. Previous studies have mentioned that depending on the EHMI types, since we have used the light strip pattern type here, these light strip pattern can be easily implemented. However, without proper training of what each light strip pattern means certain behaviors, there might be some confusion in understanding compared to other types of EHMI designs such as icons or text. So our study team have thought that that might be the reason behind why we have not seen any difference in understandability across the conditions. So to sum up this study, we have what we wanted to compare the effectiveness of the explicit communication and implicit communication. And our hypothesis was that explicit communication will show better performance in the interaction, followed by implicit communication and control. The overall results have shown that explicit communication, where the AGV is enabled with EHMI designs and the prediction algorithm, promotes better performance and subjective ratings, where it has shown less likelihood of workers entering the slowdown zone, and also higher ratings in trust, perceived safety, and performance. This kind of indicates that rather than just deploying the prediction algorithm in the manufacturing floor for the AGVs or automated vehicles, it is in order to promote trustworthy situations, it is recommended that we should also make use of the explicit communication where we use EHMI designs for the automated vehicles to convey their status directly towards the workers. It's worth mentioning there are some limitations in the study is that the VR environment was relatively simple and examined with a limited set of AGV behaviors. And also the study population may not fully represent actual manufacturing workers. Lastly, what we've thought about the future studies from this portion is that this study only focused on one-on-one interaction between one worker and one AGV. However, our realistic situation in the manufacturing facility is that there are multiple workers and sometimes multiple AGVs in the situation in a very shared limited space. So we should also definitely think about these multiple interactions, considering various interactions that could happen, and then try to kind of like make this situation trustworthy and safer in terms of human vehicle interaction. Yep, and with that, I will conclude my presentation, and I will hand over the presentation to Jin.
And everybody, we will get time for your questions after the second talk. Thank you. Keep them coming, please.
Thanks, John, for the talk. And I just want to check, are you able to see the presentation slides?
Yes, thank you.
Okay, perfect. All right, so hello, everyone. So my name is Jin. So Duan and I, we are in the same lab. So I'm happy to present another line of research from our lab, which is investigating pharmacist trust in pill verification AI system. And as I was introduced earlier, so I have a bachelor's degree from the Industrial and Operations Engineering Department, and my PhD dissertation has focused on trust and performance in AI-assisted decision making. And the reason is because, as you all are probably familiar with, artificial intelligence or AI systems have now been integrating into various domains. So some of the benefits can include it enables impossible operations. For example, in healthcare, now surgeons are able to use the technologies to perform the operations that have been impossible to do before. It can also enhance experience. So, for example, in the education domain, now students can interact with these AI agents. And in more of a transportation and defense area now, it can also help improve human decision making, where these decisions has to be made within split seconds. But the challenge here is that there is inherent uncertainty in this world that even though these AI algorithms can achieve very high accuracy under a nominal situation, there are always these unanticipated situations that will reduce the accuracy level down. So this is the reason why our lab focuses on studying human trust, which is an important variable to prevent errors and enhance collaborations between humans and AI systems. In a literature review from the NC, it highlights that trust guides reliance, especially when complexity and unanticipated situations make a complete understanding of the automation impractical. So, by that, what it means is that uh, human reliance, it leads to whether they use the system or not, which influences then the performance. So now, if you think about humans not under relying on the systems, that may lead to humans not using the AI systems, which then increases the workload. And then there may be a delayed detection of failure because now humans are not letting the AI systems verify their work. On the other hand, if humans over rely on these systems, then they may misuse the system, meaning that they may just let the automation do everything on its by itself, which may lead to skill loss, and it also leads to delayed detection of failure because um, humans are not verifying the work that AI systems are doing. So, with this information, now we're jumping into the interdisciplinary team project that our group did with pharmacy, machine learning, and human factors. And we have a lot of different sorts of papers that came out with it. But today I'm going to start focus on the trust portion of things. So, if you have been to the pharmacies and received prescriptions, you are probably very familiar with these orange prescription bottles. And dispensing errors, they occur when an incorrect drug or dose is dispensed to the patients. And these may lead to adverse drug events that it leads to 700,000 emergency room visits and 100,000 hospitalizations per year. And it also costs the healthcare system $4.2 billion annually. So, there needs to be more reliable tools and technologies to help pharmacists with this task because the medication verification is a cognitively demanding task. And pharmacists, they work under very high workload, long work hours, and this dispensing task is not their only task, that they also have to work in a distracted environment where while they're filling these pills, they may have to go interact with the patients. And another related background is that now these pill verification processes are moving from on-site only job to a remote job. So by 2021, 24 states now allowed this remote verification, which was further adopted during the COVID-19 pandemic. So you can probably see the benefit of that, that even if pharmacists are not able to be on site, we can kind of counteract the staff shortages by allowing this remote verification. And what this remote verification may look like is that first, pharmacists would receive the prescription with the reference image that shows what the prescription should look like. And then they would receive this top-down image of a filled bottle. So using this information, they can now decide whether or not this is safe to be dispensed to the patient. And we know that AI can enhance this verification because AI systems, when trained well, can perform really well in comparing between these sorts of images. So AI's integration has been more kind of, upcoming in this pill verification process. So using feature engineering, like about 10 or so years ago, engineers were able to achieve about 90% accuracy. But now using these deep learning based AI models, now these accuracy is up to about 98%. And one consideration for that is to, okay, now we have the AI system, so how can we translate it to use, design it so that we can effectively communicate with the pharmacists? So we first conducted a focus group study with pharmacists to inform this design of the AI system. So for this one, we had 8 pharmacists in 3 different rounds of focus groups. And the content that we gathered from there, we used 2 different frameworks. The first framework is the SEEPS model, which is the Systems Engineering Initiative for Patient Safety, that is widely used in the healthcare setting. And because this is a human AI interaction type of work, we also implemented this human machine teaming framework to see how these AI outputs can be effectively communicated to the pharmacists. And the graphical representations, they have been studied that it can potentially enhance trust in AI systems. So in our case, the machine learning side of project team, they developed this AI algorithm using Bayesian deep learning model. And using that, we tried to now come up with an output that pharmacists can easily look at to make help them make the comparison. So the first set of plots we have were the feature plots. So the pill characteristics of imprint, color, shape, and score. So those were considered by the pharmacists as what they would uh, really get a lot of help by these AI systems. So the AI systems, if it predicted that there is a match between the what is shown as a reference between the and the filled bottle, then it would provide a green check mark. If it predicts a mismatch, then it would provide this red X mark. And we also displayed these uncertainty histograms, and this was to display how certain or uncertain the AI model was in making these predictions. So the AI model, this Bayesian deep learning model, it generated 50 of the predicted probability for each of the image pairs. So like for each reference image and for each fill bottle, it ran that reference 50 times. And then for each of the times, it generated a predicted probability. And a figure shown on the top, it shows that there is a larger variance, which means that the AI system is less certain in this prediction. Whereas the figure on the bottom that shows a full green bar between zero point 0.9 and 1.0 that shows that the AI system is highly certain in this prediction. So we implemented these two figures in our subject testing. So for the trust portion of the things, our research question was that within varying AI performance patterns, how does the AI uncertainty information influence pharmacists' trust in the system? So by the AI's performance pattern, we used this signal detection theory to model the AI's reliability. So basically, you can think of the state of the world as if there is a signal present, which is an error, so the filled medication is incorrectly filled, and versus no signal. And you can think about this similar to the confusion matrix. And for that error, AI's response can be flagging an alert, which would be a hit, and not flagging an alert, which would be a miss. And a relation of this signal detection theory to trust is that in the past, the correct AI patterns, which is the hit and correct rejection, those have been studied to increase trust, whereas the incorrect AI patterns, which is the miss and the false alarm, they were studied to decrease trust in the AI system. And for our study, we especially wanted to focus on this miss cases because these are the potentially dangerous cases in pharmacists because these are the cases that can lead to dispensing errors as patients can receive a wrong medication. So for this experiment, we had 30 licensed pharmacists participating in the experiment. They were recruited through University of Michigan and Minnesota's pharmacy research network. And they performed an online pill verification task, which had about 82% reliability in our test. And the independent variables were AI help type, which were between subject variable. I will share that in the coming slides. And the performance patterns were within subject variable, which were based on those signal detection theory or the confusion matrix that I shared in the previous slide. So I'll just let you all take a moment to look at this slide for a bit. This is the pill verification experiment testbed that the participants looked at. So here on the left side, there is the prescription, so the reference image, along with the prescription information that highlights the drug's name and the NDC, which is the National Drug Code of the unique drug identifier. And on the right side, they received this or they viewed this top-down image of the field medication, and they sometimes received a feature plot or both feature plot as well as the uncertainty histogram. And on this page, their task was to look at all the information provided on the screen and to select whether they can accept this drug to be dispensed to the patient or they have to reject this drug to return and refill this prescription. And earlier, I mentioned that AI help type was a between subjective variable. So half of the participants were in the condition that they didn't receive the uncertainty plot, whereas the other half received both uncertainty plot as well as the feature plot. And after each of this trial, we then asked the participants how much they trust in this AI's advice. So it ranged from 0, not at all trust, to 100, which is completely trust. And here I want to highlight that the reason why we ask this after each trial is to capture this trust dynamics, which can capture how trust evolves and affects performance. So like following like correct AI trial, how would the trust dynamics or how would trust change in that sense? So we can capture that dynamic using this trust scale. So the trial procedure was that the first they looked at the screen and chose whether to accept or reject this pill. Then they viewed the performance feedback on whether the field medication was correct, whether the AI system was correct or not, and whether their final answer was also correct or not. And then they rated the trust rating. And these three steps, it was repeated for 100 trials. And instead of giving them a time limit for each of the trial, we just said for the 100 trials, the time limit that they have is 60 minutes to better reflect the real world workflow. So today I'm only going to focus on the findings of the trust adjustment. So trust adjustment is the trust rating of the current trial minus the trust rating of the previous trial. So it highlights the change in trust following each of these performance pattern. So on this figure, we have plotted on the y-axis the performance patterns, the signal detection theory, or the confusion matrix of correct, rejection, false alarm, miss, and hit. And on the x-axis, we have the with versus without uncertainty comparing between the AI help type. And for the analysis, we constructed mixed effects linear models, and we then used two-tailed t-test to compare between the AI help type. And due to time, I'm going to focus on two of the most interesting findings. So first one that I want to highlight is the miss case. So this is, again, the potentially dangerous case that could lead to dispensing error. So we especially wanted to look at this case from the beginning. And we can see here that in the with uncertainty condition, participants' trust change is significantly greater compared to the without uncertainty group. So here, initially, it may seem more kind of dangerous that their trust change is significantly greater with uncertainty. However, given the dangerous nature of the performance pattern of the miss, when AI approves this incorrect drug that can potentially lead to dispensing error, we concluded that the AI uncertainty actually could potentially help pharmacists in determining a kind of AI's uncertain prediction that leads to worse outcomes. And another interesting pattern here is that we also for the hit pattern. So here is the AI rejecting the incorrect drug. So it is actually a correct AI prediction. And historically, we found that for these patterns, AI systems, for the correct AI systems, humans usually have increased trust. But here in the with uncertainty condition, we actually found that participants' trust decreased following this pattern. And to investigate this further, that leads to one of the limitations of our study, is that we presented these uncertainty plots, and we did not control the interquartile range of these uncertainty plots, as it was an exploratory study, and that leads to the expertise. So this quote is from one of the pharmacists who participated in the experiment, and they said that it would be a little bit too much for someone not as comfortable with statistics to understand these uncertainty plots. So After finding that the hit cases led to trust decrement, we actually looked into the mean of the interquartile range, and we discovered that for the hit pattern, the mean was actually larger compared to other patterns. And we believe that this the wide range of uncertainty for the hit pattern may have influenced the trust pattern to be opposite of the previous study. And that leads to say that pharmacists, even though they're experts in their tasks of medication dispensing and interacting with the patients, they may not have as much experience with statistical representation. So that is one consideration that I would encourage us all to think about. So now, to wrap up with the conclusion, we studied how including AI uncertainty information would influence pharmacists' trust. And even though I didn't present all the results, overall, we found that pharmacists' overall trust increased with AI uncertainty information. And also, it showed that there's a potential for more appropriate trust behavior following critical AI errors. Um, However, we want to highlight the importance of AI's communication. So we have to be mindful of the user's expertise and how can AI system be implemented in these workflow so that we don't really disrupt the efficient, effective workflow, as well as how can we continue to enhance safety by not letting or by, I guess, preventing more errors from happening in the real world workflow. Um, so earlier I had said that AI has been integrating and there are challenges of these inherent uncertainty. And I just want to highlight that for studying trust and performance in human AI teams, that has a benefit that given this inherent uncertainty, we can try to have a better work environment or trying to enhance safety by studying trust and performance. So with that, I would like to acknowledge the National Institutes of Health's R01 grant for supporting this research, as well as the project team and the project partners for supporting this research. And for those of you interested in these reference, I'm sure the team will share the slides, but please feel free to email me. I'd be happy to share all these references. So yeah, that's my email. So thank you all. And now we'd be happy to answer questions for both presentations.
Excellent. Thank you, Jinyong. Okay, great. So we do have some questions that have come in for both presenters. We'll start. I think I'll just do these in order here. Duan, with respect to the magnetic bar or floor-based sensor interaction, AGVs, what restrictions have you seen with interference from surface dirt or grime, and what's used to maintain the integrity of those surfaces, and how might the AGV perform on a compromised surface?
It really depends on the actual the product that we observed for the AGV was from a specific like a supplier of the AGV called Fourier Automation, and they usually have the magnetic bars for their default. But I haven't actually seen issues with the magnetics bar with the specific situation that the question has, like the dust and the grimes and stuff. But what we could kind of infer is that the magnetic bar is used to kind of from the sensor on the bottom of the AGV to kind of be recognized where it is located. However, if there are some dirts and grimes, then I guess the sensitivity of locating where it's currently at might be reduced, and that could sometimes lead to like a wiggly motions of the AGV, just trying to figure out following the what should I say the I would say more powerful like the response of the magnetic bar. So if one portion is weak, if the signal is weak, then the magnetic bar sensor, which collects from the AGV, will try to relocate itself towards where the signal is stronger. So that could show some wiggly motions. If it still struggles in finding where it's supposed to go, then at that point the AGV will stop and then kind of gather some attention towards the workers, saying that it's having trouble relocating itself. I don't know where I'm at, and then at that moment the worker should intervene and try to relocate wherever the AGV should go.
Okay, great. Thank you. I really liked your use of virtual reality in your study, Duwan. Obviously provided some level of safety for participants and not having to interact with a real world AGVs. I was wondering though, did the vehicle announce itself in any way? Was there any audible tones emitted or anything like that?
That's a great question. That also, I'm also looking at the question where is there similarities in the instances where the subjects did not see the AGV? So we did also provide some background noises that you can hear in the manufacturing plant. Some, I guess, some like white noises, uh, um, alongside with the AGV constantly beeping sounds. So the AGV wherever it's located, you can hear the beeping sound. But like depending on how far you're from the AGV, that beeping sound could reduce and also gets louder as the AGV gets towards you. So we did provide that beeping auditory sound for the workers or the participants can notice where the AGV is currently located, even without looking at it.
Oh, okay, great. That's I imagined so. And you just touched on this that next question, the similarities in instances where subjects did not see the AGV. So what can you speak a little bit more about the common ground for that group of people that didn't see it?
Yep,
Was
I
there anything in
think
common there?
yeah, I can show like since I got lots of questions related to this, so I actually prepared like appendix slide. So yeah, I think everybody can see my screen right now.
Yes.
So these were the scenarios that we have provided with considering the direction and the crossings and the turning and the closer lane, further lane. As you can see, the scenarios highlighted with yellows are the ones that have shown high counts of not noticing of the AGVs compared to the others. And as you can see, we have went further into like the details of seeing like what's actually happening in this situation. And then for scenario 1 and 3, we can see that the AGV starting from this specific location here, and that it needs to make a turn first in order to kind of um, like join the mainstream of the manufacturing facility. So right now, the participant starts at station 1 and then heads towards 2. Here starts at station 3 and then moves on to station 4, where the direction of the VR, even though it also considers the peripheral vision as well, the VR allows you to look at those things. But even with that, like the angle of the vision, these AGVs were fairly slow, which means that they were a little bit outside of the gaze that the participants were more focused on. It also depends on the movement speed of the participants. If they move really slow, the higher that they will encounter the AGV. But some of the participants were rushing really fast and they were very comfortable in walking in that omnidirectional treadmill, which if they kind of like just rush it through towards the station, they weren't able to see these two situations. The scenario 6 and 9, usually the AGV started behind of the workers. So if the worker was faster than the AGV's movement speed, then while moving towards the other station, they didn't even get a chance to kind of like encounter the AGV unless they purposely look towards the back in order to see where the AGV is. So those were the four most scenarios that they did not notice, which is mainly dependent on the location and the environmental setup that we have designed the scenarios.
Okay. And the next question in our list here, I'll just read this verbatim. Is there something to observe from the fact that all statistically significant eHMI plus prediction results stayed around 6 to 6.25?
I guess this is due to the fact that most of the subjective questionnaires that we have given out were 7-point Likert scale. So if the participants or the workers were satisfied with the ratings, then they would kind of like answer with sevens. Then I guess if the participants kind of like were mostly satisfied or like give the higher ratings, then it will be around 6 to 7. Maybe that's why the highest result from the EHMI plus prediction resulted in around 6.0 to 6.25. But even though the other results that I have shown here showed significantly lower than the EHMI plus prediction, it is just a relative result. It is still, I guess, I would consider this as still higher ratings if we consider the 7-point Likert scale. So I guess I haven't seen any kind of like trend or specific thing to observe on the specific value of the 6.0 or 6.25, but I would say it is considered that we're measuring a 7-point Likert scale. This is a very high value amongst those scales, would be my answer.
Okay, thank you. Let's see here. Posting the question about slides, just dropped it into the chat. You can see that there's an address there. You can request those a PDF of the slides at that address. Um, okay, so there is this one's kind of long, but essentially, in a nutshell, I think it really talks about the potential of AI taking away the easier, high confidence jobs that might provide some satisfaction to a worker. Is what is that going to do to the job satisfaction in general if you know for example the pharmacist doesn't get the opportunity to do the simpler potentially more enjoyable components. I'm not sure that you could speak to that necessarily. It's maybe more of a comment, but if you have something to say on that, please do.
Oh yeah, so yeah, thanks for this question. So I mean, yeah, I am not a pharmacist myself, so like it's gonna be difficult for me to say. But one thing that I can mention is that here the easy tasks are referenced, but I believe that even with the easy task in human factors lens, there are these component of fatigue or vigilance. So even if it's easy, like, repetition of that can kind of decrease the level of, I guess, focus for the pharmacist, then that can also lead to these errors. So there may be like still a benefit that the AI systems can verify these kind of workflows in that sense. I don't know if that answered the question. So please,
Yeah,
yeah.
yes, I think that was good. The question sort of stood by itself as a comment more so I think. Um, this next one is interesting, more from a research perspective. Do you think there is any implicit bias there from your pharmacists, given that they might lose their jobs over this technology?
Yeah, so that is also slightly I guess difficult question to ask, but like my first answer to that would be our, I guess, aim is not to replace the pharmacist with it, but it's just to kind of help with help the pharmacist to achieve better accuracy. So earlier, like as I mentioned, that AI systems, like because of the inherent uncertainty, there is always like a room for error. So we believed that for this specific task, we explained to the pharmacist that this system is for AI systems to help them, not necessarily to replace them. And among the group that were recruited for this experiment, we understand that there are probably a bias in that they wanted to, participate in this experiment, meaning that they probably like to use these AI systems, but their general consensus was that even though they are slightly, I guess, worried by this, they were actually, after using the systems, they said that this can actually help them approach and help them with their task. And I, like as I spoke, like I also looked at the next question about the behavior change, and I think that's kind of like a related question. So I'll just go ahead and answer it together. Um, so I don't remember it 100% correctly, but from my memory, the the performance of the pharmacist doing the work on their own versus the using the AI systems. So for the correctly filled medication, so like when pharmacists just had to like dispense these pills and say that they're okay to be dispensed, I believe the actually no AI help was achieved better performance. However, for the cases where there were errors in the filled medication, there were significantly higher performance with AI help. So that highlights that even though like correct medication, like the performance being better with no help, like that is good. But then the with the AI system, that just means that pharmacists were more cautious with the task. So I guess overall, like the correct medications not being dispensed, that can lead to, I guess, like longer workload. However, in terms of safety, incorrect medication being correctly flagged is actually more important. So we actually found that. yeah, those are the findings for that, the second question.
Okay, so looks like we are up against time here. However, we only have one question. Well, another one popped up, of course, but I'm going to stop with this question, and that really is a simple one. For what degree has AI already been integrated into pharmacy environments? Is it currently being used?
I mean, I cannot say if these are AI systems that are being used or like automated systems that are being
Mm,
used, but there are some automated technologies such as like a pill counting or like, weighing the pills so that like they know how many pills are there, like if there needs to be, more medications in there or not. But these kind of image classifications, I believe, are still in more of a developing stages. I'm not exactly sure if it has been implemented yet.
okay, great. All right. Well, thank you so much. We'll have to wrap it up here. As a reminder, everyone who logged in today with your registration email, you'll receive a link to an evaluation form, and that'll qualify you for a certificate of completion worth one continuing education contact hour. If you have any questions for us here at COEH Northern California, you can reach out to us at coehce@berkeley.edu, coehce@berkeley.edu. And big thanks to both of our presenters today. That was fascinating stuff, I'm sure, and super timely. I look forward to hearing about next steps. So thank you, presenters, and thank you, audience, for attending today. And we'll see you at the next one. Bye, all.
Thank you all.
Thank you. Thank you.